Look, getting to the moon gets all the glory, right? That's the headline everyone cares about. But the real, nail-biting, pure engineering, that actually happens on the way back down. Today, we're diving into the absolute heart-pounding science required to bring the Artemis II astronauts back to Earth alive, and how human ingenuity manages to survive the harshest environment imaginable. So let's just shatter a massive myth right off the bat. Launching a giant rocket into space? Not actually the hardest part. While a launch is this massive, fiery spectacle, coming home is a terrifying race against a literal 5,000-degree inferno. It's a totally unforgiving environment where physics is actively working against you, and the only thing standing between 4 astronauts and total disaster is a very specifically engineered piece of material and a completely flawless sequence of events. To really understand the scale of this, you have to imagine moving so unbelievably fast that the air in front of you literally cannot get out of the way in time. The Orion capsule is going to slam into Earth's atmosphere at roughly 25,000 miles per hour. That is Mach 32. It compresses the air so violently that it tears apart and turns into a superheated plasma. You're essentially creating a man-made meteor. To put that into perspective, when spacecraft come back from the International Space Station, they're cruising at a routine 17,500 miles per hour. We do that all the time. But a lunar return? That comes in 40% faster. And that extra speed means it carries double the thermal energy. You absolutely cannot just use standard low Earth orbit heat protection for this. You need a totally different, massive class of thermal defense. So how do they survive that double dose of heat? Enter a massive 16.5-foot heat shield covered in a material called AVCOAT. This is what engineers call an ablative material. Think of it kind of like how human skin sweats to cool the body down, but instead of water, this giant shield is designed to intentionally char, melt, and sacrifice its own material to carry that extreme heat away. It literally burns itself up so the astronauts inside don't have to. Now, AVOCoat isn't exactly new. We actually used it back during the Apollo missions. But back then, technicians painstakingly filled over 300,000 tiny honeycomb cells entirely by hand. It took months. For Artemis, engineers decided to modernize it for speed. They used 186 pre-machined blocks glued right to the capsule's titanium skeleton. It sounded like a really smart upgrade, but as we found out during the uncrewed Artemis I test flight, this modern shortcut revealed a near-fatal flaw. Instead of melting away smoothly like a candle, the new AVCoat blocks suffered from something called spallation. Simply put, during that intense heat of re-entry, gases formed inside the solid blocks. Because these new blocks weren't porous enough, the gas just couldn't escape. The pressure kept building and building right beneath the surface until, pop, it violently cracked and exploded into dangerous chunks in over 100 different locations on the shield. And you know what's really fascinating? A completely unrelated flight maneuver actually triggered this whole explosive problem. During Artemis I, they used what's called a skip re-entry. Think of skipping a stone right across a pond. The capsule dipped into the atmosphere, bounced back up into space briefly to cool down, and then plunged back in. But that brief cooling period, that's exactly what allowed thermal energy to get trapped inside the shield, letting those explosive gases build up. So NASA suddenly had a massive problem on their hands. By the time they realized the skipping maneuver was causing the shield to pop apart, the Artemis II capsule was already completely built. You can't just unbolt it and start over without causing literally years of delays to the entire moon program. So how do you fix a flawed heat shield without actually touching the hardware? You have to get incredibly clever and invent a completely new flight path. Their brilliant solution was swapping from that skipping stone method to a lofted entry. Instead of bouncing, it's more like throwing a dart on a steeper, faster, and shorter dive straight in. This entirely eliminates that brief cooling off period. By keeping the heat insanely intense and absolutely consistent, the material chars away quickly and safely, completely stopping those dangerous gases from ever accumulating in the first place. Problem solved. But hey, in engineering, nothing comes for free, right? The steep dive fixes the heat shield, but it comes with some incredibly heavy trade-offs. It gives mission control a much narrower landing zone out in the Pacific. It cuts their launch windows in half, making it way harder to find the right time to fly. And most intensely, the astronauts inside have to endure a crushing 3.9 Gs of force. Imagine having nearly 4 times your own body weight violently pressing down on your chest. The final, nail-biting countdown begins at exactly 400,000 feet above the Earth. This is where a 13-minute survival clock officially starts ticking. The European service module, the part of the ship that provided all the power and life support for the whole trip, detaches and burns up. From this exact moment forward, those 4 astronauts are completely alone in the Orion capsule, relying 100% on the physics of their heat shield. As Orion plunges deeper, that compressed air we talked about turns into a terrifying plasma sheath. We're talking about a 5,000-degree wall of glowing ionized gas completely swallowing the ship. It's so intense it actually blocks all radio waves. Mission control goes completely dark, no communication whatsoever. But miraculously, thanks to that ablative shield, the cabin inside stays at a perfectly comfortable 70 degrees. After a few agonizing minutes of pure radio silence, the capsule finally slows down just enough for the plasma to clear out, and Mission Control hears the crew's voices again. Whew! But wait, they are not safe yet. Orion is still plummeting toward the ocean at 325 miles per hour. Hitting the water at that speed would be like smashing into solid concrete. This is exactly where the most complex braking system ever built takes over. It is a perfectly choreographed 10-minute dance of 11 different parachutes. First, small chutes pull the roof off the capsule. Then, 2 drogue parachutes fire out to stop it from tumbling. Next up, 3 pilot parachutes shoot out, and their only job is to physically yank the incredibly heavy main parachutes right out of their bags. It has to be totally flawless. And those 3 final main parachutes, they are absolute marvels of engineering. Each one is a massive 116 feet across, made of a highly durable Kevlar and nylon hybrid, and weighs over 300 pounds. Together, they act like giant brakes in the sky, aggressively dragging that fatal 325 mile per hour freefall all the way down to a gentle, survivable 17 miles per hour right before hitting the water. When those giant parachutes finally lower the crew into the Pacific, Navy divers stationed on the USS John P. Murtha will be waiting. It perfectly echoes what Artemis II flight director Jeff Reitigan called 13 minutes of things that have to go right. But here's the crazy part. Popping open that hatch and seeing the astronauts wave is really only half the battle for this specific mission. Because immediately after the rescue, the Navy is going to haul that blackened, scorched capsule straight back to the Kennedy Space Center. There, engineers are going to meticulously map every single crack, every burn mark, and every missing chunk of that shield. They have to prove, without a shadow of a doubt, that their steep dive mathematics actually worked. If the shield looks exactly how they predicted, it officially clears the path for Artemis III to land humans on the moon. So you have to ask yourself, is a safe crew enough to call it a total success? Well, the astronauts might come home completely unharmed, but the silent, charred scars left on that heat shield, they hold the ultimate answer. Those scars will literally dictate whether the entire Artemis program continues to the moon or if we have to go all the way back to the drawing board. Getting to the moon is the headline for sure, but surviving that journey home, that is the true masterpiece of engineering.